If I was to say that I was in a train traveling at 30 kilometers per hour, and I was to walk forward in the train at 10 kilometers per hour, what would be my velocity relative to the ground? Okay, I can walk at 10 kilometers per hour. Okay, that's actually a jog, actually, but let's say I'm walking or jogging at 10 kilometers per hour. That's how fast I can go. The train is moving at 30. What's my velocity relative to the ground? What's the answer to that? What is it? 10? So my train is going at 30. I'm walking at 10. My velocity relative to the ground would not be 10. It would be either 40 or 20. 40 or 20. What's the difference there? Why 40 or 20? Depends on which way I'm going. If I'm walking towards the front of the train, it's going to be 40. If I'm walking towards the back of the train, it's going to be 20. How did I do that? Well, I added vectors together, right? I added 30 meters plus 10 meters. That gave me 40 meters. Or I added 30 meters and 10 meters. That gave me 20 meters. Does that make sense? When you're finding relative motion, relative velocity, and relative motion, you've got to add vectors together, always. If I'm on that moving walkway at the airport, you know what I'm talking about, right? If I'm on that moving walkway at the airport, and it's moving at 3 meters per second to the right, and I'm moving at 3 meters per second, if I can walk at 3 meters per second, I'm walking on that moving walkway in the right direction, then my velocity relative to that store over there in the airport is 6 meters per second. I added those vectors together. If I'm walking opposite because I'm waiting 2 hours for my flight and I want to entertain myself by walking the opposite way on the moving walkway, then my velocity is going to be 0 meters per second. I'm going to appear to be stopped, right? How did I do that? I added vectors. 3 plus negative 3 gives me 0. You ever run up a down escalator? Yes? Everybody's done that. If you haven't, then you haven't lived if you haven't run up a down escalator. The escalator is moving down at 4 meters per second. You're running up at 5 meters per second. What's your velocity relative to somebody that's standing there watching you and saying, some old person standing there watching you saying, oh, those darn kids shouldn't be doing that. What's your relative velocity there relative to that person? It's going down at 4. I'm going up at 5. What's my relative velocity? 1. Right? 4 plus negative 5 gives me 1, or 5 plus negative 4 gives me 1. You see how I do that, guys? When I'm trying to find a velocity relative to something, I add vectors together. Well, what if I have a problem like this? What if I have a problem where I'm driving my car north at 100 kilometers per hour, but there's a wind blowing my car to the east at 20 kilometers per hour. And I'm not compensating for this, right? I'm just letting it go. Whatever happens, happens. What's going to be my velocity relative to the ground? Where's my car going to go? Well, I have to add these vectors together, just like I did before, right? Except this time, we're not going to say 100 plus 20 is 120, or 100 plus 20 is 80. We're going to have to add these vectorially using the skills that we've learned over the last couple of days, right? In that case, we'd say 100 to the north plus 20 to the east gives me a resultant velocity. By the way, that should be kilometers per hour. Gives me a velocity relative to the ground of r. We were adding displacement vectors together. Well, we can also do that with velocity, right? Exactly the same thing. And we know how to add these vectors together now, so we're able to solve these relative motion problems now. Now, I'm going to change this. Now I'm going to change this from this solid line to a dotted line here. Now listen carefully to what I'm about to say. This dotted line is the sum of the vectors. This dotted line is what happens as a result of the other two vectors. So I call it a resultant vector. The other two vectors, my solid line vectors, contribute to what happens. My dotted line vector is what happens. Does that make sense? So now I'm going to categorize those solid line vectors and dotted line vectors to make these word problems, these word relative motion problems a little bit easier. First of all, I'm going to say solid line vectors occur in vectors that contribute to the overall motion. So in that example that I used, right, the way that I was aiming north, that contributed to my overall motion, right? The wind, was that my overall motion? No, the wind contributed to my overall motion, right? The wind contributed to where my car went, so that would be a solid line vector as well. My dotted line vector is my overall motion. If you go back to that example, that dotted red line is where I actually went, where my car actually went. Now, more realistically, you're probably, if the highway is going north, if the highway is north, and you got a wind to the east, then you're probably going to aim somewhere northwest, right? So my solid line vector would be northwest, my solid line vector would be to the east, and then my dotted line vector would be straight north. You ever drive, how many people drive a car here? How many people have a license? You know, like we get winds sometimes, wicked winds in Alberta, right? Chinook winds. And sometimes it's like you look at your steering wheel and it's like this, right? You have to aim in a certain direction as a solid line vector in a certain direction to get your dotted line vector to go straight ahead. Make sense? Right? We just intuitively do that, but today we're going to learn to mathematically analyze that. All right. So solid line vectors contribute to the overall motion. Dotted line vectors are the overall motion. Okay, they're where I end up actually going, my overall relative motion. Examples of solid line vectors would be where I aim or head. If I aim to the north or if I head to the north, then we would say that would be a solid line vector because that contributes to where I actually go, right? It's not where I actually go. It contributes to where I actually go. If there's a wind speed, I don't go in the direction of the wind, but that contributes to where I go, right? If I'm in a boat or I'm swimming and there's a river current to the east, that doesn't mean I go to the east, but that certainly contributes to where I go. Whereas my dotted line vector, my overall motion, my relative motion, question might say, where do we actually go? Where do we actually go? What's my relative motion or my relative velocity? My velocity relative to the ground. All of those are dotted line vectors because all of those are where I actually go. My velocity relative to the ground is not contributing to where I go, it is where I go. My relative velocity is where I actually go, not contributing to where I actually go. There's one more I should have put in there under solid line vectors actually. How many people when they've flown in an airplane have taken that magazine out of the seat back when you're supposed to be listening to the safety instructions, right? Yeah? Okay. You're listening to you're supposed to be listening to the safety instructions. You take that magazine out and you're kind of flipping through that magazine. You should pay attention to the safety instructions, by the way. Take that magazine out and you're reading it. And at the back of that magazine, sometimes, depending upon the airline, they list the different planes that they fly. And they give the statistics like the wingspan and the length of it and the number of passengers. And another one they give is the airspeed. The airspeed. That's the speed that the airplane can fly in the absence of a wind. Sometimes it's like about 900 kilometers per hour. Okay, so you could fly at 900 kilometers per hour in the absence of wind. That doesn't mean that's the velocity of the plane, the actual velocity of the plane. but that contributes to the velocity of the plane, right? The airspeed of the plane contributes to how fast the plane goes. Let's do one example here, guys. One relatively straightforward example. Captain of a ship aims his ship north at a speed of 10 meters per second. Current in the ocean is to the west that's carrying it off course. What's the ship's resultant velocity? So let's think about solid lines and dotted line vectors here. What contributes to the motion? What is the motion? Captain of the ship aims his ship north at 10 meters per second. Do I draw that as a solid or a dotted line? Is that contributing to my motion, or is that my actual motion? Ashley? Yes. Like, I'm not actually going north, right? I'm trying to go north. I'm aiming north. That's contributing to my motion. So I'm going to draw that as a solid line vector, 10 meters per second to the north. Now, there's an ocean current that's 2 meters per second to the west. Is that where I'm actually going west? Do I actually go west? No, that contributes to my motion, right? Now, where am I going to draw that? Remember, when you have two things that contribute to motion, you have to add them together to find the relative velocity, right? Just like we did in that train example, in the moving walkway at the airport example, and the escalator example, right? We added the vectors together. We got to add these ones together as well. But how do we add these ones together? We have to draw a vector diagram. Where are we going to draw the two in order to make this a good vector diagram? Head to tail. There's a couple places I could actually draw it. Does this work? Absolutely it does. Absolutely. Now, that's where I'm going to draw it. But would this have worked? No, because that's not drawn head to tail. Hold on one sec. Would this have worked? No, not drawn head to tail. Would this have worked if I had drawn it right here? Yes, it would, because that's drawn head to tail. Hold on one sec, guys. Now, my resultant vector is going to go right here. Whoops, going to make that a dotted line, though, because that's my actual motion. That's where I actually go. Now, you're going to solve for that value of r by doing the Pythagorean theorem, and you're going to solve for theta. We draw it right here at the start of the vector diagram, as we always do. No different than we've done over the last few days, right? And we're going to solve for theta using the inverse tan function of opposite over adjacent. You good there?